In lesson 6.2, Volumes of Solids of Revolution using the disk method, we'll explore our first foray into finding volumes of solids of revolution, which is perfectly analogous to what we did in our last section when we found areas of regions between two functions. In 6.2, we'll take a region, it might just be defined by a curve or by a series of curves, and we'll revolve that region to create a solid of revolution. We'll take a look at a couple examples of those so it makes some sense. But once we have that down pat, we're going to use this thing called the disk method in order to find the volumes of these solids. The basic idea is simple. We're going to slice these solids into billions and billions and billions of little circles that have essentially no height, but certainly, of course, have a radius. If we find the area of each one of those circles and then add them all together, what we'll have is the volume of our solid of revolution. So we'll take a look at a few of these. Sometimes our solid of revolution has a hole in the middle. We'll see some of those. And when that's the case, we have to use this thing called the washer method, which is essentially two disk methods, one that's good and one that gets removed. So we'll take a look at the washer method, and then we'll finish up this lesson by looking at special types of solids that are created using geometric shapes that are built perpendicular to the plane of the region. So it all sounds very confusing, and it is at first. But once we take a look at a few examples, I think this will make a lot of sense. And all that being said, before we get started, let's first take a look at the formula in which we will find the volumes of these solids of revolution. Let's take a look now. Now, before we get into the formulas to find these volumes of solids of revolution, let's first talk about what a solid of revolution looks like. More often than not, we'll be given some function or another. Let me go ahead and create a function that I'm going to call f of x here. And we'll be told where we're rotating this function around. For this particular example, let's say we're rotating it around the x-axis. Now, if we do that, what's going to happen is that function will essentially be mirrored. But there's more to it than just that. Not only will the function be mirrored, it will be mirrored in such a way that we're actually looking at a solid here. This is a three-dimensional construct that's made by rotating this function around. And so this is a solid. And I tend to draw an open circle like this, an ellipse, so that we can see that it is, in fact, have height, width, and depth. Now, how are we going to find the volume of the solid? This is actually very easy. What I'm going to do is I'm going to construct a rectangle that is perpendicular to the axis of revolution. In this particular example, the axis of revolution is the x-axis, and so I'll build a rectangle that goes up from the x-axis to the function itself. Now, if this rectangle were to get rotated, hopefully you can imagine that what it would do is create a disk of sorts. It would look like that. Now, what would be the width of this particular disk? Well, there's going to be millions and millions and billions of these disks. And so really the question is, what is the width of each one of them? In this particular case, the width of each one will be dx. All right? So that's essentially negligible. All it's saying is that the width is so minute that I can add an infinite number of these up, and they will sum together to give me my volume. Now, the real question is, what is the radius of one of these disks? And hopefully you can look at this and see for yourself that the radius is actually just going to be the function itself. In the most basic case, of course. It does get more complex, but for the time being. So let's say I were to create another disk, maybe this disk right here that I've been toying around with. If I do that, again, it will have a width of dx, but a radius of the function as well. So at all points along this curve, the radius of each disk will be the function. So how's that going to help me? Well, what I'm really just finding is the area of each circle, and then adding all of them together throughout the interval that the solid exists on. So in a case like we have here, where we actually have a horizontal axis, all we're really going to need to do is to add up all these circles, which of course each have a volume of pi r squared. Now r, of course, as we said, is the radius, so we'll have pi r squared, and then of course dx. Now this will go from the beginning of the solid to the end of the solid, of course. And to be quite honest, this pi right here is a constant and can be moved outside of the integral. So if we have a vertical axis that we're rotating around, it's going to be a very similar formula. This time I will move the pi outside. We'll integrate from a to b of the radius of each disk, which of course is just the function itself, and then times dy for the height of each disk in this particular case. So you can see that really all we're doing is pi r squared. That's really all it is, pi r squared. The only difficulty comes in what is the actual radius, and that's where we're going to spend the majority of this lesson focusing on. Now, it does sometimes happen that we do have a hole in the middle of our solid. Let me just draw one as a quick example. Let's say that we have this particular function, and we want to rotate it around the y-axis. Of course, as you can see, if we rotate it, it'll look something like this. And while the bottom is perfectly fine, no issues here, and the top is perfectly fine, notice that we do have this blank area in the middle, essentially a hole. Well, if that happens, our disks are not going to go all the way to the axis of revolution. Rather, what we'll have is this capital R radius, which is the outside function, and this little r radius, which is the inside function. And so what we'll have in that particular case is pi from a to b of the outer radius squared minus the inner radius squared. And that one I should call little r of x. Now, don't let this confuse you. It really still is pi r squared minus pi r squared. So we do need to square the radii separately, but we'll see a couple examples of those as we get to them. So with all this explanation aside, let's go ahead and take a look at example A, where we will have the most basic form of a solid of revolution around an axis. Let's go ahead and take a look now. In our first example here, if you take a look at your notes, you'll see that we have a figure that is made by the graph given there, y equals the square root of 16 minus x squared. I drew the graph for you, and here on the screen you can see what this graph would look like if it were rotated around the axis. Now what I'm going to do is go ahead and not just show you this graph, but also play around with it a little bit. If I were to rotate it quite a bit so you could see the top of the graph, that's what it would look like. And let me go ahead and put it back to the way it was. Now, if I want to find the volume of this solid, there really is no simple geometric formula to do this. So what I'm going to do is I'm going to slice this solid with horizontal circles. And I'm going to make those circles go from the top all the way down to the bottom, as you can kind of see here. Now, using the calculus, of course, I'll go from bottom to top. But really, I'll end up with the same volume either way. So those are all the circles. And here I go back up again. Now, the problem is it's kind of hard to see these circles. So maybe if I go ahead and tilt this solid a little bit, you'll see the actual disk that this lesson refers to. Now, that disk is a circle. And here are a bunch of the circles that compose this solid. All I'm going to need to do is find the area of each one of them, add them up, and I will have the volume of this solid. Let's see how this is done. So now that we've seen how this entire thing looks in concept, let's take a look at the calculus of this in application and see how everything works out. First off, our picture is drawn here of our region, and the first thing that I like to do quite often is to actually complete the drawing. If I'm going to be rotating it around the y-axis, as is specified in the problem, what I'll get is a solid that looks kind of like the solid that we were just looking at in those animations. Now, this representative rectangle here, it will of course turn into this disk, and this disk is simply a representation of all the disks that compose this solid. So I'm just going to go ahead and draw this disk right here so I have something to look at. Now, the first thing I do need to ask myself is, well, how tall is this disk? How tall is it? And clearly it's very, very, very small. In fact, I'm going to call it dy in height. In other words, it's essentially nothing. It's infinitesimal. It's dy. But the importance of that is it sets up that this entire problem has to be in terms of y. If the height of this disk is dy, I can't go having things in terms of x. And therefore, I'm going to have to solve this equation for x. And if I do that, what I'll get is that x is actually the square root of 16 minus y squared. You should be able to do that algebraically yourself. Now, is the radius really the square root of 16 minus y squared? Well, a good way to test this is to check the radius at the top and bottom of the solid. In other words, when y is 0, what should be the radius of that disk? Take a look at the picture, not the equation, but look at the picture. When y is 0, you notice that the disk should have a radius of 4. Well, plug 0 in for y, and what do you get for your radius? You get 4. So that works out. Let's see, what should be the radius when y is 4? That's this disk at the very, very, very top. And hopefully you say to yourself, well, if y is 4, the radius of that disk would actually be 0. Plug in 4 for y, and if you get 0 for your radius, then things are looking good. And let's go ahead and use this as our radius. That is the distance from our axis of revolution to the function itself. So if we go ahead and set this up, what we're going to find is that the volume is pi times r squared. Here is my radius, 16 minus y squared. I will square that, and I'll include dy essentially as the height. In other words, if you want to think of these as cylinders, it's not traditionally done that way. But if you like, we have pi r squared h. Again, there's our pi, r squared, and then dy can be the h. But it's essentially 0. Where are we going to start and where are we going to end these circles? Where they're going to start at the bottom, where y is 0, and they'll end at the top, where y is 4. And if you notice, we can simplify this right off the bat. Because we have the square of a square root, we can simply call this 16 minus y squared dy. Now, I'm not going to go through the process of integrating this and using the fundamental theorem. You should be able to do that on your own by this point in time. But if you do work this out, what you should get is a volume of 128 thirds pi. And if you want to decimalize that out, if you will, that's approximately equal to 134.041 cubic units. And so what we have done here is we've taken a region, we've rotated it, we found representative disks along the way, the top and bottom. We found the radius of each of those disks, and we simply set up our pi r squared and include the h if you like. From there, we just integrated and find that the volume of this solid of revolution is as you see there. So all that being said, let's take a look at one more example. I'm going to skip the entire rigmarole of the animation and just skip straight to the work. So please join me here in example B. In example B, we're going to begin essentially the same way that we began example A, and that's simply by drawing the solid of revolution that we're trying to find the volume of. Now, we're given this region right here that's made up of these two functions, and we're told that we are going to rotate this around the x-axis. So there's my arrow of revolution. Now, if I do this, notice that it's quite interesting. This doesn't actually go down to the axis of revolution, but what I'm going to do is attempt to draw a reflection of this region, and maybe it'll look something like this, more or less. And what I'm going to do is when I rotate this, I'm essentially going to get a bead kind of shape. It's going to have outer parts on it, but it's going to have this inner cylinder that's basically missing. So if you think about a bead, you can pass a string through the center of it, and that's basically what we have going on here. Now, this representative rectangle that's been drawn for me, we'll rotate to this rectangle right here. And so you see we have this issue going on where we don't have a complete disk. Rather, it seems like we have what we call a washer. And really all a washer is an outer radius and then an inner radius that's removed. So we're going to have to handle that when we're setting up our integral here. Anyway, hopefully that's not too bad. We're still going to integrate if we want to find the volume. It's still going to be pi times the integral from the beginning to the end, which I'll talk about in just a moment, of my outer radius squared. And in this case, what is my outer radius? Well, of course, it's going to be this right here, while my inner radius, or my little r of x, is going to be this right here. And so my outer radius is actually going to be this 4 minus x squared over 4. And I'm going to have to square that outer radius. And then I will subtract my inner radius, which in this case is actually just 2. And I'm going to square that as well. Now, is this going to be a dx or a dy? Well, hopefully it's going to be a dx since I've already set everything up that way. But take a look at the width of this washer, and you'll notice that it is definitely a dx. So all is good as far as that's concerned. Now, I do need to discuss my my lower and upper bound here. I know it kind of looks like my lower bound is at x equals -3, but I'm going to argue that that's not necessarily the case. What we need to do is see where do these two functions hit each other. And so if I set these two functions to be equal to each other, all I really need to do is solve for x, and I'll find my lower and upper bounds of integration. And in fact, if you do that here, I'm going to skip all the algebra. But what you should get is that x is equal to positive or negative square root of 8. And so those are going to be my lower and upper bounds. Now, it might be kind of difficult for me to fit in this small space. But there's my lower bounds, negative square root of 8, and positive square root of 8 for my upper bound. So this integral looks like a hot mess. But what I'm going to argue is that it can be simplified quite well if I just square both parts, the outer and inner radius, and then combine like terms. I think what I'm going to end up with is actually just going to be 12 minus 2x squared, and then plus x to the 4th over 16. So really, that's not that bad of an integral to do. And for that reason, I'm going to skip all the calculus that's involved here. And what I'm going to get is approximately 132.694. Now, for those of you who do want to do it by hand and come up with the exact answer to this should be 448 square root of 2 over 15. And, of course, don't forget your pi. So there you go if you want to do it by hand. This is the exact answer. This is the approximate volume of this. But look what was involved. We couldn't just square the outer radius. We had to treat this as a washer. So we squared the outer radius. That essentially gave us the full solid of revolution. But then we subtracted the square of the inner radius. All that did is removed the inner part, which in this case ended up just being essentially a cylinder. But be very, very careful when you do this. You must square the outer radius and square the inner radius separately, and then combine your like terms and integrate from there. So that's how the washer method works. It's just like the disk method. It's just that we have an outer and an inner radius. So with that, let's go ahead and take a look at just a couple more examples. We'll start with example C, in which we're not going to be rotating around an axis. So we'll learn how to handle that here in example C. So here in example C, we're once again given an equation, this time y equals 1/2 x cubed. We're looking at the region bounded by that, by the line y equals 4, which is this dashed line I've drawn right here, and by the line x equals 0. So we're looking at this region right here, this almost triangular region. But notice that this time we're going to rotate it around the line y equals 4. So we're not rotating it around an axis this time, but rather this dashed line. What will our solid of revolution look like? Well, if I draw this correctly, which is a rare case, and I probably didn't, but approximately right, what we're going to have this time is a solid that looks kind of like this. This time it's rotating this way. So you see what it looks like. If I were to draw a representative rectangle in order to help me find my radius, my rectangle might look something like this. Now, of course, if I rotate that, this is going to be the disk I'm looking at. And it's nice that the disk doesn't have a hole in it, so I don't need to worry about using the washer method here. But what I need to do is I need to look at it and say, am I dealing with a dx problem or a dy problem? And clearly, if I look at this circle, the radius is going up and down, but the width of it, or the height, if you will, is in this case going to be a dx kind of height. So everything needs to be in terms of x's here. Now, what is the radius of this disk at any point between 0 and 2? That's a little bit tougher. I can't just say the radius is 1/2 x cubed. I can't do that. But rather what I could say is that it appears my radius is actually going to be 4 minus 1/2 x cubed. Where did I come up with that? Well, 4 is my axis of rotation here. So I can start with that and then actually subtract the function. And what we should do is just check this to see if it actually makes sense. Certainly I've made mistakes on this, and you probably will as well. So do this little check. When x is 0, what should be the radius? Well, when x is 0, that's going to be the bottom, if you will, of this entire solid. And it looks like it should have a radius of 4. Well, if we plug 0 in for x, what is our radius? It's 4. So that's good. Finally, we should check one more thing. What would the radius be if x is 2? Well, for that one, go ahead and plug 2 into x, and you'll see mathematically the radius is 0. So this provides some good evidence that this radius is in fact true. And since that's the case, let's go ahead and set up our volume formula. The volume will be pi from 0 to 2, since our circles are starting at 0 and going up to 2. And, well, we're just going to do our radius squared. As we said, our radius is 4 minus 1/2 x cubed. And we'll just square that, multiply it by dx, and we should be good to go then. So if you want, you can go ahead and square this out, do your simplifications, do what you have to do. But if you do this correctly, what we should get is that this solid has a volume of 144/7 pi, or if you want a approximation for this, about 64.627 cubic units. So, you see how it's done when we're not rotating around an axis. We just need to think a little bit harder. But usually what it ends up being is that the radius is simply the axis minus the function. That doesn't work 100% of the time, but it's always a good place to try. Always remember to try the beginning and end of your intervals into your radius to see if the radius actually comes out the way that it should. In this case, it did. That was pretty sweet. And that will set us up for example D, in which case, not only are we rotating around somewhere that's not an X or Y axis, but there's a hole in the middle as well. So this will kind of bring all of it together in a very beautiful way. Let's take a look at example D. All right, so example D is a fun and exciting problem because, as I said, everything is going to come together here. First off, what we need to do is take a look at what region we're rotating. It's a very common assumption to just pick a region and rotate it, but a very bad assumption as well. So in this particular case, we're taking the region bounded by the this red line here, as well as y equals 0 and x equals 0. So that's going to be, let's see, x equals 0 and y equals 0. So it is going to be this triangular region right here. And what it says is that we're going to rotate this around the line x equals 6. So we're going to rotate it this way. And if we do that, this x equals 0 is just going to turn into x equals 12, essentially. Y equals 0 will still be y equals 0. And this diagonal line will actually turn into this diagonal line. And so don't just look at it as two triangles. What we really have here is a solid of revolution that is essentially a cylinder with a inverted cone removed from the middle. I'm going to try to draw this as best I can, but you've gotten used to my drawings by now, and you know they're not very great. So, actually, that one's not too bad. There we go. You can see all it is a cylinder with the inverted cone removed out of it. And that's what we want to find the volume of. Now, let's be honest with each other. Using the geometry that you already know, you could probably find the volume of this without using any calculus at all. In fact, I encourage you to pause the video and try finding the volume yourself using geometry formulas. You should know the formula of a cylinder and the formula of a cone, so that shouldn't be a problem. But as for the calculus, let's go ahead and draw a representative rectangle here. And I'm going to draw it right here. So here is my representative rectangle. If that is rotated around, it will rotate to over here. And you can see that clearly we're going to have to be dealing with a washer method because the region doesn't butt up against the axis of revolution. If I go ahead and attempt to draw this, you'll see that it has a hole in the middle, essentially. And the disc, or the washer rather, will look something like this. And excuse my drawing, but you can kind of see it hopefully for yourself. The middle, of course, is a hole, and so this doesn't exist, and I'm just looking for the ring there, or the washer, if you will. Now, all that being said, I think so far we're looking good. But what we do need to determine is this a dx or a dy type problem? Well, the height of this washer is going like this, and this is going to be a dy height. You can see that as we stack them, each one has a height relative to its y. So there's dy. We do need to determine the outer radius, which will be a function of y, and the inner radius, which will also be a function of y. Now, the outer radius should not be too difficult at all. No matter where I am up or down on this figure, the outer radius is always going to be 6, no matter where I draw this washer. So the outer radius is simply going to be 6. That's nice. That's easy. How about the inner radius? Well, I'm given the equation y equals 6 minus x, but I really need that in terms of y. So why don't I call this x equals 6 minus y? That's just a little bit of algebra trickery there. And by doing that, I can now say, well, my inner radius is simply going to be my axis of revolution minus my function. And of course, that can be simplified, and you can simplify yourself to just come up with y. So, very interesting. Our outer radius is 6. Our inner radius is y. Let's see if that even makes sense. If we pick a washer at the very bottom of this figure, what is its outer radius? Well, its outer radius is 6, so no problem there. What would its inner radius be when y is 0? Well, its inner radius wouldn't really exist. That would be 0 as well. So y is 0. That works out. Now, at the top of this solid, when y is 6, what would the outer radius be? And of course, that hasn't changed. That's still just 6. But the inner radius should, looks like it should also be 6. And if I plug 6 into my inner radius, well, I get 6. So both of these do look good. I can now calculate my volume. That will be pi from 0 to 6. That's from the bottom to the top, 0 to 6, of my outer radius squared minus my inner radius squared. And I'll multiply that by the height of each washer, which is dy. And this is perhaps the easiest integral we've had yet. It's not the easiest problem, not by any means, but it is the easiest integral, which is funny because the hardest part of these problems is simply setting up the integral. Well, if you do set it up correctly and you do work this out, what we should get is that this solid here has a volume of 144 pi, which is approximately equal to 452.389 cubic units. So, if you tried doing this using geometry formulas, hopefully you came up with 144 pi yourself. But if not, calculus to the rescue. There we go. It is correct. It does work. It wasn't even that hard once we got it set up. And that's what it's all about. So, for our last example, we're actually going to switch where we are, and instead of looking at volumes of revolution, we're going to look at volumes that are built up by using figures perpendicular to the plane. Now, this sometimes gets a little confusing. There's a lot of models out there that you can play with to kind of see this. But let me go ahead and draw a few examples for you before we get into example E. Before we begin our example dealing with cross-sectional solids, it might be a good idea for us to take a look at what is meant by a cross-sectional solid. In these four examples that I've drawn out here, I've given you a region, and in each example, I've stated what type of figure is represented by the cross-section of the solid. In the first one, we're dealing with squares, and what we're going to do is we're going to build these cross-sections perpendicular to the x-axis, just without loss of generality. Now, instead of thinking of this graph as being on a wall, I actually want you to consider that this graph is on the floor, and we're actually building the figure up from this region on the floor. So pretend like you're looking down at this. Now, if I'm going to build a bunch of squares on here, perhaps my first square will be really small and will look like this. Now, this is a rather tiny square, but notice that its base edge goes from the top of the interval to the bottom of the interval. I will do that again right here, but of course this square will be much, much larger, simply based on the fact that its base edge is much larger. And as we move on, this one will be even larger still. So you can see that these cross-sectional solids are strongly relative to the actual interval that they're given in. Now, as we move further on down the x-axis, the squares will begin to decrease in height, and that's simply because their base edges are decreasing, and eventually we'll get to the end of this interval where the square is again tiny and even smaller still. So it's rather difficult to draw these types of pictures, but just think of them as these cross-sectional shapes, whatever they are. And in this particular case, this is what my cross-section will look like. It will be a square, and not a very good one that I've drawn there, but hopefully you get the idea. Let's take a look at a couple more of these. I'm going to run through these rather quick. If we're dealing with semicircles, then of course, once again, we'll have something like this, where the diameter is based on this region. And as we move towards the center in this particular region, the semicircles do increase. And as we move away from the center, the semicircles again decrease. And on the two edges, the semicircles are tiny. Now, do we know how to find the area of a semicircle? That is going to be extremely important. Of course, the square is simply the side squared. The semicircle is actually going to be 1/2 of the side, which you could refer to as the diameter if you like. So 1/2 of the side, we'll square that, and that will be the r squared times by pi. So it's really pi r squared. But then, of course, because we're dealing with semicircles, we'll have to multiply that whole thing by half. Essentially, just find the radius and go pi r squared with it. Now, if we're dealing with right triangles can be a little bit tricky sometimes. If we build it like this, and we know that this is a right angle, then there is a right triangle. Here is a larger right triangle. Again, it's still a right triangle, though. Here is going to be the largest right triangle. It's giant. Of course, being a right triangle isn't enough. What problems will often do is tell you that it's a right isosceles triangle. And that way you know that whatever the base edge is, the height will be that same value. And so here are a bunch of right triangles, and my solid is essentially going to look like this. Now, the last one we're going to look at will be the equilateral triangle. I will clue you into the fact that the area of an equilateral triangle is actually the square root of 3 divided by 4 sides squared. I'll leave it to you to prove that to yourself, but equilateral triangles, very much like their right triangle counterparts, will vary in size based on their base edge length. So here we go. It is different than right triangles. Notice I'm not drawing any right angles in here. but it does look like this. And again, that top edge might go something like that. So that is what these cross-sectional solids essentially look like. And now that we have an idea of that, I strongly suggest that you go on the internet and look some of these up. Of course, there's better drawings on the internet and interactive Java applets that you can play with to really see these visually. But now that we have the idea at least, now let's go ahead and take a look at example E, where we will be dealing with equilateral triangles. Fun and exciting. So now that we've seen what's meant by a cross-sectional solid, let's go ahead and apply that knowledge here in example E, where we're given this region bounded by these two graphs in red and the y-axis, x equals 0 here. Now, according to the problem, we're going to build a series of equilateral triangles that are all perpendicular to the x-axis. Our first step really should be to attempt to draw this solid that we're going to try to find the volume of. Of course, as we get closer to x equals 2, these equilateral triangles are going to be very, very small. But as we get closer to x equals 0, these equilateral triangles get larger and larger and larger. And so eventually we end up with a picture that looks kind of like this. Notice that each triangle seems to be bigger than the last as we head to the left. And we end up with this crazy looking picture here. Now the top of this solid will look approximately like this. The end of the solid will be this equilateral triangle at x equals 0. And of course, it's bounded again by these two graphs. So here is essentially what our solid looks like. It's a bit of a mess, but hopefully you can kind of envision. Again, put this region on the ground and look down at it, and this should be the picture you see, a series of equilateral triangles rising up at you. Now, all we need to do is find the area of each of these equilateral triangles and add them all up from x equals 0 to x equals 2, and that should give us the volume of this cross-sectional solid. Now, we don't need to deal with pi in this case, because remember, pi is when we were dealing with disks and washers, which are circular. Here we just have equilateral triangles. So again, we'll integrate these equilateral triangles from x equals 0 to x equals 2. And these are x's, of course, because each of these equilateral triangles has a width of dx, if you will. And so, as we discussed in the previous part, each equilateral triangle will have an area of the square root of 3 over 4 times s squared. Now, all we need to do here is figure out what is s. In other words, how long is each side? Well, we can tell that based on this the region down here. And it looks like, well, each one is simply going to be 2 minus x. And where did I get this 2 minus x? Well, that's simply the difference between the top graph, which is 1 minus x over 2. So we found the difference of that minus the lower graph, which is negative 1 plus x equals 2. And if we go ahead and work that out, of course, 1 minus negative 1 is 2. And negative x over 2 minus positive x over 2 is simply minus x. So that is the side length of each equilateral triangle here. And so this is our volume formula for this. Of course, the square root of 3 over 4 is a constant, so I can move that out. And I am left with this, 4 minus 4x plus x squared if I go ahead and square my binomial. And all I need to do is just integrate that. Now, that's not a very hard integral to do at all. In fact, if I do it correctly, I should get 2 square roots of 3 over 3, or approximately 1.154 cubic units. So that is going to be the volume of this cross-sectional solid. Now, imagine what would happen if instead of equilateral triangles, we had used squares. Well, if we had used squares, the problem would actually be a lot easier. We'd go from 0 to 2 of the sides squared. We just would leave out the square root of 3 over 4. It wouldn't be necessary if we were just doing squares. Or imagine if we were doing semicircles. What would be the radius of each semicircle? It would just be half of 2 minus x. That would give us the radius. So we could square that, multiply by pi, and integrate all kinds of good stuff. And that's how you do the volume of a cross-sectional solid. So, here in lesson 6.2, we've covered one major topic, but it was very, very, very major and involved a lot of parts. So I'm not going to sit here and say that this was easy. It takes a lot of practice to get it right. But our first step should always be to draw the solid of revolution, if it is a solid of revolution that we're dealing with. Simply draw the picture. Once you've done that, draw a representative rectangle on the 2D picture, which will turn into a representative disk, or washer, if you will, once that region is rotated. Determine whether we're dealing with a dx or a dy, because that will guide the rest of the problem. Once you've determined dx or dy, get everything in terms of that variable. Try to determine the radius, and by try, I mean actually do it. Determine the radius of each of these disks or washers. If it is a washer, of course, you'll need to determine the outer radius and the inner radius separately. And once you've done that, all you need to do is apply the volume formula, which is the volume equals pi times the integral of the radius squared. Of course, if we're dealing with a washer, it's pi times the integral of the outer radius squared subtracted by the inner radius squared. And don't forget about your dx or dy. Once you've done that, integrate it, and there you go. There is your volume. We also took a look at cross-sectional solids, in which case the first thing you should do again is try to draw the picture. Once you've done that, determine the area of each cross-section. And we looked at that if they're squares or triangles or semicircles or what have you. Find the area of each cross-section, and then the volume will simply be the integral from beginning to end of the area of each cross-section. Now, I'm not, again, saying that this is easy. It does take practice, but with enough practice, it will become a lot easier for you. And for that reason, keep these notes handy while you're working on your assignment for 6.2. And as always, good luck.